Good afternoon, everyone. On behalf of Olympus, my name is Greg Ristabin. I'd like to welcome you all to this webinar on XRF as part of a reasonable testing program for consumer product regulations. This webinar is a joint venture with Intertek and Olympus Innovex. We have on the panel today Jishen Chen and Brendan Connors from Olympus Innovex and Joe Langton from Intertek. This webinar should last approximately 45 minutes with 10 to 15 minutes or so at the end for a Q&A session. If you have questions, please type your questions in the Q&A panel. Now, without further ado, I'd like to turn this event over to Brendan Connors from Olympus Innovex. Brendan, it's all yours.
Thanks, Greg. So most of you who are attending today are affected in some way by regulations of consumer products or hazardous substances in consumer products manufacture. Today we'll be giving you a state of two of the big regulations, RoHS and CPSIA. We'll talk about how, as a manufacturer or importer subject to regulation, you can set up a testing plan to help mitigate the risk associated with regulation. And lastly, we'll cover use of XRF as a screening method, especially as part of a production testing plan. Also, I just want to mention that nothing in this webinar should be construed as any sort of legal advice. We'll go over the regulatory landscape and talk about key elements of a testing program, but every manufacturer's requirements are different, and we're not making specific recommendations about what any individual should have in their testing plan. And so first I'll turn things to Joe Langton from Intertek to tell us about his company.
Thanks, Brendan. Again, Joe Langton from Intertek. If you don't know Intertek is a global company. We concentrate mainly in testing, product and process certifications, and consulting. We have laboratories globally, worldwide, over 1,000 labs and more than 100 companies. And we work with Olympus Innovex using their equipment in many of these facilities, as well as putting in programs within companies worldwide for substances. The group I work for is the Health and Environmental Group. We concentrate mostly on restricted substances, global directives and laws, whether it be REACH, RoHS, CPSIA, or any type of green claims, life cycle assessment, and any design for the environment issues.
Okay, and to introduce Olympus Innovex, Innovex was founded in 2001 as an analytical instrumentation manufacturer. We specialize in XRF and XRD testing equipment, primarily for in situ analysis, meaning that we provide instruments where the testing is needed. The emphasis is on developing applications where you can bring the analyzer to the sample rather than have to bring the sample to the analyzer. Innovex has been part of Olympus since 2010. We're part of the Analytical Instrumentation Group. Our headquarters is just outside of Boston, Massachusetts, and we have over 10,000 XRF analyzers in the field for a whole range of applications, including especially for consumer products testing. And now Jishen will give us an update on the current state of RoHS and CPSIA.
Thanks, Brendan. So today we will focus on two regulations updates, RoHS recast and CPSIA. First, let's have a look at RoHS. As we all know, RoHS, the restriction of hazardous substance in electronics, was adopted in February 2003 by the EU and took effect on July 1, 2006. Both the original RoHS and its recast include the same 6 elements and compounds for lead, mercury, hexavalent chromium, PBBS and PBDS, the brominated flame retardant. The restriction level is 1,000 ppm. While for cadmium, it has a much tighter level in 100 ppm. For RoHS, the recast, one of the most noteworthy changes will be the 2 of the existing weak categories, Category 8, medical devices, and Category 9, monitoring and control equipment. These 2 categories have been previously benefited from exempt status, but will be brought into scope 3 years after the date of entry into force of the recast. Also, pay attention to the Category 11. This new category serves as catch-all, Because of this very broad categorization, one should refer back to the existing definition of electrical and electronic equipment and realize that anything not explicitly exempted from the VISCO would be subject to RoHS under the provision of the recast. Also, the recast provides a specific timeline for compliance, such as for Category 8, medical devices and monitoring and control equipment. Member states shall ensure the compliance of products placed on market after July 2014. For Category 9, they should be in compliance after July 2017. Products in Category 11 have 8 years after the date of entry into force to comply with RoHS, which is 2019. Next, let's have a brief review on CPSIA. So last year, CPSC decided to drop the lead content limit to 100 ppm in August. Since then, there were 2 more related final rules have been approved. One is conditions and requirements for relying on component part testing rule. The other is testing enabling pertaining to product certification rule. Within this rule, the third-party testing rule is the center of the discussion. The component testing rule mentioned that the responsible parties may issue a CPC, Children's Product Certification, or GCC, General Conformity Certification, based on the component reports or certifications. So the finished product could be certified partly or entirely based on the test reports for the individual component. For instance, if you manufacture children's clothing with zipper and your zipper supplier has certified them for lead, you can use the report to support your certifications on the finished product. But remember, when you apply this rule, you should exercise your due care, which means you receive, review, and ensure the appropriateness of the documentations. Also, you need to keep the record and make sure it is traceable. In addition, when there is a material change, such as change in design, manufacturing process, or suppliers, you need to recertify the product. For third-party testing rule, it's only applied to the children's products which are designed or intended primarily for children 12 years age or younger. It covers toys, children's clothing, and a few other product categories. So you may ask, who are responsible for the certifications? So only importers and domestic manufacturers are the 2 parties who are responsible for the GCC or CPC. When you look at the chart, you could find children's products must undergo third-party testing, while non-children's products can be certified via a reasonable testing program. To ensure continuing product compliance, it is required that the children's product be sent to the lab periodically. The minimum required testing interval will vary based on what other periodic testing procedures are in place. If you have no other periodic testing in place, which means you are only controlling your risks by sending the samples to the lab, the maximum testing interval is up to 1 year, while it is 2 years if you have a production testing plan or reasonable testing plan in place, and the maximum every 3 years if you have an in-house ISO or IEC accredited lab. Of course, a number of factors listed in the regulation will have an impact on your final decision. So, why do you need a reasonable testing program? As shown, a reasonable testing plan can be used to certify for non-children's product under CPSIA, can help assure compliance and demonstrate due diligence for RoHS. At the same time, it helps you control risks and save costs for children's product testing. The CPSC guidance documents, as we mentioned before, the testing enabling pertaining to production certification rule mentioned that you might send out fewer samples if you create finished products that are uniform in composition and quality to provide a high degree of assurance of compliance. To achieve that, reasonable testing program could be one of your options. And again, you could send the samples to the lab with less frequencies with an RTP program in place, which can save you both time and money, most importantly, control the risks. Of course, the cost saving effect here is subject to a list of factors under the rule. Other than CPSIA and RoHS, reasonable testing plan can be applied to many more important regulations around the world. such as California Proposition 65, EU REACH, etc. So next, Joe Landon from Intertek will talk about the detail of RTP. Joe?
Thanks, Jen. So the next section of the presentation, we're going to talk about the steps involved in putting together a reasonable testing program. Part of those steps is we want to define the goals and the criteria and then outline the process steps. So the overall goal of a reasonable testing program is to provide reasonable assurance that the product or the end product or the material meets all applicable requirements, not only existing safety or customer requirements, but also new requirements related to restricted substances. And how can we implement XRF and utilize it as part of this program? We recommend that all elements of an overall compliance scheme should be part of an existing quality management system or an environmental management system. Your supplier management is a key step into this any testing process. Part and component compliance is always the responsibility of your supplier, but you need to assess your supplier's risk to determine what needs to be tested because of any gaps in the supplier control. The three main steps or elements of a reasonable testing program is assessing requirements, verifying those requirements, and then making your claims if your product is green or any type of eco labeling or marks that you require on your product. As far as assessing requirements, we want to make sure we assess not only customer requirements but also regulations specifically for restricted substances. It is key, again, to know your supplier's process for assessing restricted substances as well. Once we get into the verification and certification step, we want to know what material needs to be tested. If your supplier does not have a robust system or cannot produce compliant documentation, testing will be needed at your facility or at a subcontract lab. We also make sure we have to choose the proper test methods and inspection techniques, and everything also needs to be documented as far as procedures and processes. Once these steps are in place, we can then better make claims to our product is green or any environmental claims that their requirements have been designed to. Additional elements under assessing requirements and verifying steps, we need to understand the additional elements and criteria to develop the process steps required for a RTP. We need to supplement what is known about our components and material. Is there a risk that a restricted substance is present? Can we test components further upstream in the supply chain to reduce the cost of final product testing? And again, what is the frequency to mitigate as much risk as possible? We need to select the best techniques for testing. We recommend starting with XRF for screening because this may enable you to reduce most costs as far as lab testing at a final product stage. And again, always follow standards. There's test methodologies that are available. They are published by the IEC or CPSIA, ASTM, whatever your requirements specify. So again, to summarize the criteria for a testing program, again, we need to provide reasonable assurance that the product meets all requirements. We need to determine the type of testing that is needed. XRF screening is used to detect restricted substances. Lab testing is always used to confirm inconclusives based on our XRF screening. Defining frequency depends on the type of material and product, and always used methods and procedures that are industry standard. Additional requirements that you may apply to your product or material. Product specifications. Always use product specs to determine what materials may contain a restricted substance and compare these specifications to applicable safety rules, whether they're CPSIA, RoHS, or whatever other standards that may be applicable. We also want to assess market and customer drivers. Does the customer have a specific restricted substance list that he requires you to test or be compliant to that defines substances beyond CPSIA or the RoHS requirements? Once the criteria and the requirements are defined and understood, process steps can be developed. On this slide, these are the steps we recommend. They may not be applicable to every situation, but we feel that these are the proper steps needed to put in a reasonable testing program. Identification of applicable requirements. Again, we spoke of market drivers, regulatory requirements, and possible RSL if necessary. Always have procedures which we refer to as a compliance assurance system or process within your own manufacturing facility as well as within your supply chain. Employee-vendor communication and training is always key as well as supplier data collection. Gap assessment is always performed as part of our program within the supply chain as well as manufacturing facilities. Once these steps are implemented and we have a robust system, we can then be assured that we've done the best due diligence to make our product claims. Reasonable testing programs should always be part of what we call an overall compliance assurance system. The compliance assurance system is very similar to existing quality management systems or EMSs that you may have in place in your organizations. We recommend that reasonable testing procedures should always be implemented into the product realization process, which is defined by the ISO standards. Moving on to specific types of tests that are required or may be part of your program is production testing. Production testing can be component testing before final assembly and may contain XRF for screening. If certification testing is needed, this requirement would fulfill any needs for the IEC, CPSIA, or GCC requirements as needed as well. Always make sure corrective action is available as well in case they're in a plan for containment and root cause analysis. And again, always document process steps. Specific types of testing that we use when we're doing a reasonable testing program, of course, we spoke of XRF screening. XRF is the best method for screening for RoHS heavy metals, whether it be for RoHS or CPSIA for lead, and also for the presence of bromides. But again, chemical testing must always be part of your program to verify any inconclusives as a result of your XRF screening. There are also small off-the-shelf methods that you can use for screening techniques for heavy metals, chromates, cadmium, and lead. Again, chemical methods must also be used for quantifying any of the heavy metals when XRF results are inconclusive or when there's uncertainty in the reading using your XRF. These test methods are always in a laboratory environment, are the best, and have the lowest detection limits available. Another additional test when testing for phthalates. Okay, phthalates are a requirement under CPSIA for children's products. XRF cannot detect phthalates. Lab testing is the only method that's available for detecting phthalates in your product. A real-life example that we use every day here within Intertech as part of our Greenleaf program, and it is an example of a reasonable testing program. It's a very simple process, three-step process, where we review documentation from suppliers. We assess bombs, drawings, material declarations, and test reports. If we identify any high-risk substances as a part of this review, we then move that on to a testing phase. We always do a process audit. The process audit identifies gaps in when substances are processed. XRF is always used to detect restricted substance within material as well as contamination on a production floor. Third step is always lab testing to verify any inconclusives or detect any substances that XRF has limitations in detecting. And then once we complete the process, we can issue our certifications once we're satisfied with the results. So at this point, I want to hand it back to Brendan, where he's going to talk more about the XRF equipment and how it can be used within the testing program.
Okay, thanks, Joe. So as we've heard so far, the verification step in a reasonable testing program includes a few key elements such as auditing, certification testing, and screening. Screening usually takes place in the form of a production testing plan that's deployed based on a manufacturer's assessment of risk. When drawing up a production testing plan, a manufacturer or other responsible party has to decide what samples will be tested, what kind of testing will be done, how frequently testing will be done, and what will be done if a failing test is found. All of these are decided based on analysis of risk. So where are you most likely to catch failures, and what is your greatest exposure to noncompliance? Among the testing methods that are available for production testing, XRF is the most powerful tool that's likely to be used in-house. Most manufacturers don't have an in-house wet chemical lab available for testing in most cases. So we've talked a bit about XRF now. I think many of the attendees are familiar with XRF already, but for those who aren't, what is XRF? XRF, or X-ray fluorescence, is a technique for measuring elements in a sample. The principle is that if you expose a sample to X-rays, the elements in the sample will send X-rays back at different energies. The X-rays that go into the sample come from an X-ray tube, which you can sort of think of as a light bulb for X-rays. The X-rays that return have, from the different elements in the sample that go back to the analyzer, have different energies or wavelengths, which you can think about as having different colors. It's not exactly the same thing, but the analogy sort of holds. A detector in the analyzer collects all of these X-rays, and software on the analyzer can translate that information into what elements are present and how much of those elements are present. The user sees a readout on the screen on the analyzer or on an attached computer on what elements are present and the concentrations. The readout might look something like this. So what this means is XRF is a pretty powerful and non-destructive technique to identify and measure the elements in almost any sample type. If we start with a periodic table of the elements like we have here, XRF can be used to measure any element that's highlighted here from ppm levels on up, starting with magnesium on up. This makes XRF useful in production testing, where regulations like RoHS are directed towards restricted elements, lead, cadmium, mercury, and other hazardous elements. XRF is well suited to detecting those elements in a variety of materials. So let's say you're considering XRF screening as part of your testing program, or you have an XRF analyzer already, but you want to use it more effectively. There are a few things you want to keep in mind before you get started. First, you need to determine what you're going to test. So to determine that, you want to start with the items of biggest risk. Where is XRF most likely to find non-compliant materials? You'll want to look for materials that are likely to contain restricted elements. Just to give a few examples, some brass alloys may have, some grade specifications have percent levels of lead, or lead can make it into alloys as an impurity in some of the raw materials. They might be an area you'll focus more on. Solders are materials that historically have contained lead in different formulations. Plastics that have high recycled content may have a greater likelihood of containing restricted elements than virgin plastics, depending on sourcing. I don't mean to pick on any of these materials. Risks vary based on what kind of products you're making, but these are just some of the examples of things you'd want to look for in deciding where to focus your efforts in production testing. You'll also need to determine screening levels. The XRF analyzer will give you a ppm or percent result for the elements that are present, but you need to decide how that result will translate into a pass or fail decision for that part or material or component. There are standard methods available to help you with that. As Joe mentioned, IEC 62321 is a pretty common one that gives some guidance on how to set up screening levels based on XRF results. And here's an example of one that's specifically for testing of homogeneous plastic materials under the RoHS regulations. So the IEC also recommends having a buffer zone around your screening levels, and that's known as the uncertainty budget. That's what the IEC document calls it, the uncertainty budget. The uncertainty budget is the sum total of all of the limitations of your technique, limits on sample preparation, limits based on what calibration you're using, may include possible user error. And if your result falls within that area of uncertainty, you may need to do additional testing in order to ensure if your product is compliant or be sure your product is not compliant. Notice also that bromine and chromium are treated differently in this testing scheme. Bromine and chromium, again, this testing scheme is for RoHS specifically. Those two elements are not restricted elements. They're restricted in certain chemical forms. So chromium is restricted as hexavalent chromium, and bromine is restricted in certain flame retardants. XRF can tell you the total elemental content for these elements, but it can't tell you what chemical form they're in or what molecules they're bound in. So you can use XRF to pass you can use an XRF to result for those elements to say that a sample passes if you have a very low result for those elements, but if you detect higher levels of those elements, you may need to do some additional testing. So there are a few merits to using XRF as well as some cautions that we'll go over. First of all, XRF testing is quick. Your testing times are on the order of seconds to minutes, and you test for multiple elements simultaneously. This fast testing allows you to have higher sample throughput. You can test more samples by XRF than you could by most other methods. And faster testing means you get faster turnaround of results, and you can make decisions faster based on those results. XRF is non-destructive, so you can preserve a sample for further testing, either to send to a lab, or if it's a case of high-value manufacture, you can still sell the product after XRF testing. XRF allows you to test in situ, which means that you can take your XRF equipment onto a production floor in a warehouse. You can test fixed equipment, and if you have multiple manufacturing locations, you can move the analyzer around. XRF can be used by non-technical users. The day-to-day operation doesn't need to be done by someone who has a technical background. We do recommend that any end user who purchases an XRF analyzer have a standard operating procedure in place for using the analyzer to make sure that it's being used correctly and that the results are being interpreted correctly. But the day-to-day operation doesn't need to be done by someone with a technical background. Results from XRF testing can form the basis of compliance documentation where third-party testing is not explicitly mandated. So this doesn't apply to children's products under CPSIA, but it does apply to non-children's products where you can produce a general certificate of conformity based on a reasonable testing plan where XRF is a part of that testing plan. So there are a few challenges, cautions, and caveats to using XRF as a screening technique. XRF is a surface technique. It's measuring the surface layer of your material. The penetration varies based on what kind of material you're looking at. But if you have a restricted element that's buried deeper in your sample, you may not detect it by XRF, or you might detect it at lower amounts. XRF is an elemental testing technique, so it's great for testing lead, cadmium, and other restricted elements, but as Joe mentioned, it's not compatible with testing phthalates in materials or finding out what kind of flame retardant you have in your material. You need to use other testing methods to get that information. You want to be familiar with what detection limit you are going to be seeing for your sample type and make sure that your screening level is realistic based on that detection limit. So as an organization, as part of your production testing plan, you'll decide on what screening levels you want to go with, but you want to make sure you can reach those with the kind of XRF equipment that you have and the kind of samples that you're testing. Detection limits do vary based on what kind of sample you're testing. You also want to make sure you understand the materials that you're testing and the regulations that apply. You want to know what your action levels are and what the exemptions are, if there are any. There's another example. RoHS has some exemptions for certain materials. For example, steels have a higher lead exemption limit than the standard 1,000 ppm. And so you want to make sure that you're applying the correct action level to the material that you're testing. You want to know the capability and limitations of the particular equipment that you have. There are a couple of specs about XRF equipment that I'll go over briefly. The X-ray tube in the analyzer that produces the X-rays operates at a given voltage, and the common ones that you'll see are 40, 45, or 50 kilovolts. This mainly has an impact on some heavier elements, specifically cadmium and antimony, and a few other elements, but cadmium and antimony are the two big ones that are of concern in consumer products testing. And your tube voltage, your maximum tube voltage, will have an impact. For other elements, including bromine, mercury, lead, and a few others, tube voltage doesn't have as much of an impact on the detection limits you can reach. The detector in the analyzer, there are a few different kinds that are common. Probably two of the most common you'll see are the silicon drift detector, SDD, or the PIN diode. The SDD is a bit newer technology. It has better sensitivity, higher performance. It can reach to lower detection limits than the PIN diode can. This is especially of help if you're doing testing of a lot of metals. Usually detection limits are for different elements are higher in metals than they are in lighter materials like plastic, and so the SDD will help you a bit more. The PIN diode still works for a lot of applications, but you want to make sure that the performance level that you can reach is going to match what your screening requirements are. Also, you want to make sure that you're operating the analyzer safely. It is an instrument that's based on using X-rays, and the instruments can be used safely. They're used safely every day, but you want to make sure that proper procedures are being followed so that users aren't exposing themselves or others to X-rays. Probably the biggest challenge in interpreting XRF results is looking at inhomogeneous samples. So the analyzer's calibration normally assumes that the material being tested is uniform and the elements detected are distributed homogeneously. When testing a material made up of multiple different materials, the XRF result may not represent any one material tested. So in order to deal with that, you want to test at the homogeneous level as much as possible, as high up in the production stream as you can. For inhomogeneous samples, your results are usually qualitative. You can see what elements are present, and you can judge how much relative to other similar sample types, but the ppm result that you see on the screen may not apply to any one material in that sample. Sample thickness can have some effect on your measurement, mainly by raising detection limits when samples are very thin. The IEC document that I mentioned earlier has some recommendations for minimum sample thickness when testing by XRF. For plastic materials, it gives a recommendation of 5 millimeters minimum thickness, so you don't want to go any thinner than that. If you do, be aware that your detection limits may be higher. It's also very helpful to understand how your instrument is calibrated. XRF instruments usually come with several factory-installed calibrations for different material types, and so you may need to validate that calibration on your own sample types. Now, you can do this with reference materials, certified reference materials, or CRMs for your sample type, but there are a limited number of CRMs suitable for XRF compared to the total, the volume of different sample types that people want to test with XRF. And this is one place where lab testing can be a big help in complementing XRF. Most XRF analyzers will allow the user to adjust the calibration based on their own real-world samples. And so if you have an independent test result from a lab for your own samples, you can adjust the calibration to make sure that the XRF response matches whatever your independent test says. In XRF, we're usually looking out for what are called matrix effects. These are the effects that most of the elements that are in your sample are having on the few elements that you're actually looking for. Sometimes elements can interfere with each other, can raise detection limits, or cause deviation of results. The software normally takes care of all of these, a calculation software that comes with the analyzer, but there are some cases you may want to be aware of what's going on. Just as an example, if you're testing for lead in brass alloys, some grades of brass alloys contain high bismuth content. Because of some line overlaps, an alloy with high bismuth content will have a higher lead detection limit than an alloy with no bismuth content. And so if you see detection limits changing like that, that's one thing to look for, matrix effects, what kind of interferences are present. So XRF screening complements lab testing in a lot of ways. XRF allows for testing a much greater volume of samples than you could test by a lab. Cast your net wider, look wider for non-compliant products. But at the same time, lab testing allows users to validate their XRF testing approach and make sure that proper procedures are being followed and that the correct decision, pass or fail, is being made based on your XRF results. Also, XRF results can become part of documentation. Most instruments will allow you to print a test report based on the results that you got, and if your instrument has equipped with a camera, it can save a picture of the sample as well, so you can see what you tested, and for a larger item, precisely what location you tested on the sample. This can become part of your product documentation and can be useful down the road to demonstrate due diligence in testing if you should ever need to do that. So here are a few examples of places where XRF might fit into a reasonable testing program. With incoming part QC, you specify ordering compliant parts from your vendors, but for new suppliers or for parts that contain materials that have historically been more likely to contain restricted elements, you may want to scrutinize those more closely. XRF is useful for inventory control. If you're ordering parts, similar parts that are both compliant and non-compliant, you can make sure that they've been sorted appropriately. This is mainly of concern if you're a manufacturer who's operating compliant and non-compliant manufacturing streams. This is less common than it was a few years ago just because of the prevalence of environmental consumer products regulation in the last few years. But if you do have multiple manufacturing streams, you can make sure parts are being sorted appropriately. XRF is useful in process control. If, for example, if you check your raw materials and they are free of restricted elements, but somehow restricted elements are being added to your product somewhere along the production stream, XRF is useful for pinpointing those sources, checking heavy machinery, checking chemicals and solvents, trying to find out. I've seen cases where the raw materials don't contain any restricted elements, but somehow they're introduced along the way because of some procedure that's being carried out. XRF can be used as a final QC check, test products before shipping. If you're manufacturing low volume production, then you may be able to test every product you send out the door by XRF. With higher volume, you may do a more random sampling. And for a larger item, larger component with XRF, you can test multiple locations, multiple materials. And so we're commonly asked what kind of detection limits can XRF reach down to compared to what the regulations are. And so this is just a very broad overview of what a typical XRF analyzer can reach, and this is based on a few of our products at Innovex. And so you can see roughly what detection limits an analyzer can reach down to in different materials. You can see that for metals, it's higher than the detection limits are higher than they are for plastics. And also I mentioned earlier about the X-ray tube voltage that you're using, 40 kilovolts versus 50 kilovolts. It's mainly helpful for certain heavier elements that have they have higher energy emission lines. And so if the tube voltage will mainly have an impact on that. It won't, 40 versus 50 kV won't have as much of an impact on the other elements. Again, these are typical LODs based on ideal homogeneous samples. They do vary based on application, so but this is just to give you a broad overview of what sort of performance XRF can reach to. And with that, I thank you all for attending. I hope you enjoyed our talk about testing programs, regulation, and XRF. And we're happy to take any questions that you might have. I actually see quite a few have come in already. Okay, so I see one question here on can we provide any information about sampling plan for testing? As part of, I assume this is part of a reasonable testing program, should that only include testing high-risk parts or medium-risk parts from high-risk suppliers and certain numbers or lot numbers from certain suppliers? Joe, is that something you'd be able to address?
Sure. Yeah, so I guess it's very difficult to kind of paint a broad brush over sampling plans, but typically what we like to do is, in my case, if it's any risk, I don't like to use medium risk myself. If there's a chance of risk, then I test the product or test the component. I don't tend to classify them into three classes: high, medium, and low. It's just it's risk or there's no risk. And typically, we like to use sampling plans that will enable us to sample at least one product in the batch. We like to go back to, if anyone remembers old AQL, melt standard AQLs, we would use a normal AQL at about 10. To make sure we test at least one product out of a batch. When we get up into higher batches, again, we'll test a few more samples. But again, we want to make sure we have enough data, collect enough data or statistics to then claim that the product is compliant and I can take it off that high risk list. So again, if any more information is needed on that question, you can always email me or anyone in the panel here. We can get some more information for you as far as specifics.
Okay, so we have another question on what types of product characteristics cause inconclusive results with XRF screening. There are a couple different cases where you can get an inconclusive reading that might require additional follow-up testing. And also, just to stress, the inconclusive band needs to be decided by the manufacturer or whoever is setting up the production testing plan. It may be different for different manufacturers based on the different kinds of samples that they're testing. But a couple of examples of an inconclusive result are a result that's very close to your legal action level. So the screening guideline that I showed earlier has a recommended broad uncertainty belt of about plus or minus 30% around your action level. So if you're testing a sample for lead and you see the action level is 1,000 ppm, if XRF gives a result of 900 ppm, that's close enough to the action level that you'd want to do some kind of confirmatory testing to ensure that see if the product is compliant or not compliant. Also, if you're testing for say for bromine and you test very high levels of bromine in your sample by XRF, that's going to be determined as inconclusive because the XRF sees the bromine present, but it can't tell you what chemical form the bromine's in, and so it can't tell you if that product contains the particular flame retardant that's restricted by RoHS. As far as the element, if you're testing an element that's very close to the action level, just on a practical level, if the sample actually has 900 ppm of lead in it when your legal action level is 1,000, and that particular homogeneous material has 900 ppm, yes, it's compliant, but you also need to ask, do you really want to be accepting parts from that supplier that are so close to the legal action level? Does the supplier know how the lead is getting into that material, and is there any way they can mitigate that? So yes, it's true that that's an inconclusive XRF result, but you also sometimes need to take a step back and ask, do you really even need to be in that situation to begin with? The question about the surface effects of materials that are on the surface affecting XRF results. If the results on a metal can be affected by residual oil on the surface, or this comes up a lot with any sort of surface coating, it really depends on what the surface coating is and what elements you're looking for. With residual oil on the surface, it's usually not going to be a problem for most of the heavier elements that you're testing for, but if the oil contains wear metal content from some other source, that can interfere with the results. It's usually best to clean your sample surface before testing, but there are a lot of cases where you can test through a very thin surface layer. So the short answer is it's better to have a clean sample to be safer, but you may find there are cases where you don't have to clean the sample based on your own testing. We have a question about error measurement from the XRF analyzer. So the analyzer, when you're testing by XRF, the analyzer provides a measurement and an error. The error is the uncertainty on the measurement, and you get an uncertainty, you see an uncertainty reading on any kind of analytical measurement you ever take. Any kind of analytical instrument will have some sort of uncertainty associated with it. And that's the repeatability of the measurement based on it's based on statistical analysis. If you're familiar with the concept of sigma, that's your 1 sigma uncertainty. So it gives you some idea of if you run multiple tests on a sample, how much will the next result vary. If you get one test that's 500 ppm, the next test probably won't be 500 ppm exactly, but it may vary. It will vary based on what the uncertainty is on that reading. The question on what would the process look like to screen an average laptop, time, number of samples, etc. Joe, is that something?
Yep. So we've worked on similar situations, and it really depends on what you're looking for. Again, when you're screening a laptop or a printed circuit board that's already soldered and complete, it's going to be very difficult to get down to the level of the components once they're soldered. The small spot size is 3 millimeter on the Innovex device, and you're not going to be able to test down to that level. So you're going to be able to screen for the certain substances, whether it's lead or cadmium, but you may get some inconclusives based on the material, such as ceramics, which do contain lead, which have exemptions under RoHS directive. But we can screen a laptop, we can screen a computer or a printed circuit board. A typical laptop may take, depending on what we're looking for and how many shots and how granular we want to get, anywhere from an hour to 2 hours, and then to do the analysis of what we found, it actually takes a little bit longer than that to prepare a report and do the analysis. But again, it's going to be a combination. I would suggest using a combination of XRF material data sheets that you have from your suppliers, and as well lab testing. So that's going to be that's going to be part of a reasonable testing program where you use all three methods.
Okay, for testing of stainless, nickel, and duplex alloy steels with high levels of chromium, what tube voltage is going to be preferred or better for that kind of testing? Of the options that I mentioned, 40, 45, or 50, that's the maximum spec for the tube voltage. It's not going to matter much for chromium analysis. The voltage spec is just the maximum on the tube, and the tube can always be run at lower voltages. This is something the user usually doesn't have control over. That's set up within the analyzer's software. But as far as the maximum tube voltage spec between the ones that I mentioned for chromium testing, it's not going to make much of a difference. We have a question about how long are we required to keep records? Joe, is that
under the recast, the RoHS directive, we're going to be required to keep those for 10 years. And I believe the CPSIA is just as long. We recommend once you ship a product into the field that you keep those records on file somewhere for at least the life of the product if you can in the field. But the requirements I know under the RoHS directive is 10 years under the new recast. CPSIA. If Zhaijian has that information, maybe she can specify that.
Yeah, for CPSIA, I believe it's for 5 years right now.
Okay.
So you don't need to translate everything in English, but you have 48 hours by request. So basically, you need to keep all the records for 5 years.
Okay, we have one question about XRF. Does the temperature of the sample affect results? Generally, no. XRF, the instrument will have some temperature range that you can use it within, but the actual temperature of the sample doesn't affect it. There are a lot of different applications for XRF. We've been focusing on consumer products testing, but it is possible to test alloys, in-service pipes, for example, at oil refineries that are hundreds of degrees Fahrenheit. You have to run very quick tests, and you have to take some appropriate precautions to insulate the analyzer, but it is possible to test those, and that's to make sure that the correct alloy of pipe is being used. It's a completely separate application, but the short answer is no. There's no effect of sample temperature on results.
There's a question regarding if the product has a layer of oil that contains a heavy metal contaminant, should that be and shipped to the customer that way? Should the sample be cleaned before testing? Typically, this would be considered two homogeneous substances, the oil and the alloy, and both should be tested separately if possible. The XRF can be used to screen the entire product to determine if there's a substance there. Again, if the heavy metal is detected, we would not know that was coming from unless the oil is separated. So if possible, if both homogeneous substances can be separated before screening them, that would give you better conclusive results. The question as far as handheld XRF and warehouses receiving products from overseas, such as China, perform random scans. This is one excellent application for XRF because it is portable. You can screen product before it is shipped. It may save you some cost if there are any infringements or substances detected. And I know this is one of the major applications that it's being used for right now.
I see a good question on what's the main difference in operation between an isotope scanner XRF equipment with cobalt-57 source versus an X-ray tube. I only talked about X-ray tube XRF in this talk. It is also possible, instead of using an X-ray tube, to use an isotope source to produce your X-rays. there are a few drawbacks to using an isotope source. You actually have a radioactive material in your analyzer, which means there's a different set of, in most states and most countries, it's a different set of regulatory requirements that you have. There are, in some cases, greater restrictions on travel with the analyzer, and there are some disposal concerns with using an isotope source. We don't see isotope sources being used as much for consumer products applications. A lot of that has to do with the regulatory requirements where manufacturing is going on in so many different countries, and they're in a lot of places the requirements are more stringent. As far as performance difference between those, an XRF, a tube-based instrument, an isotope source is always running at one particular energy, and an X-ray tube has a maximum energy, but it's adjustable over a whole range. So that generally gives you, that in most applications can give you better sensitivity over a whole range of elements. The question about packaging material, how do you test packaging material for scanning? This is another restricted substances regulation that we didn't talk about. There are packaging directives in Europe where the sum of elements, chromium, mercury, lead, and cadmium have to be less than 100 ppm. One of the most difficult things with packaging materials is that your samples are really thin. So I mentioned earlier that there's a recommendation for plastics. Your samples should be at least 5 millimeters thick, and in a lot of cases you want to try to go even thicker than that if you can. So the first thing I would say with testing packaging materials is if your sample is very thin, you're testing cardboard or plastic wrapping, try to make a thicker sample as much as possible, and you can do that just by stacking multiple layers or wrapping it up a bunch of times. That you may see a great improvement on the results that you're seeing. Okay, so I see one question that came in early on, is there any danger to operators using XRF? Is there any need for certificates for using handheld XRF? And I addressed that a bit in my talk, but because XRF is a technique that relies on using X-rays, you need to make sure that you're using it safely, but it can be used safely. Whichever vendor you purchase from will give you some sort of information about safe operating procedures. You usually don't want to have anyone else within 1 or 2 meters around you. Certainly you don't point it off in the air. You don't point it at other people, and you don't want to have your hand near the analysis window. But as long as proper procedures are in place, you can use it. You can use it safely, and with proper use, the risk of exposure is no greater than any number of other things you do during the day. As far as the need for any certification for using handheld XRF, it depends on what state. It varies by state and also by country. Your local vendor can give you more information about specifically what's required. Some places are more arduous than others. I also see another question on, can we use XRF for analysis of a ceramic? And I see another one on, can we use XRF to test liquids? There are a number of sample types you can use XRF for. I've focused on plastics and metals here, but there's not really any limitation on what kind of sample you can test. Basically, as long as you can put it in front of the analyzer, you can test it. The limitation is what you're testing for. So it needs to be an application that tests for elements, and they need to be higher than the minimum detection level for an analyzer. I see one question on lithium testing in aluminum alloys, and the short answer is no. You can't test for aluminum. With handheld XRF, the lightest element that you'll see that you can test for is magnesium, so anything lighter than that wouldn't be possible. And I see another question on using XRF as a surface technique. What's the depth of measurement? It's going to vary based on what kind of sample you're testing. For light materials like plastics, your penetration depth for the X-rays will be millimeters up to centimeters, so it can be rather deep in the sample, but it depends what elements are present in that plastic. If it's a heavier plastic with maybe a few percent of zinc as an additive or titanium, or certainly bromine as part of a flame retardant, that penetration depth is a lot smaller. For metals, for aluminum, a lighter metal like aluminum, the penetration depth is on the order of millimeters. For most other heavier metals, from titanium on up, your penetration depth is on the order of microns, only tens of microns for the densest metals and maybe hundreds of microns for some of the lighter metals. I see a question about portable XRF used for geology applications. We're only covering consumer products here, but there's a whole range of applications you can use it for, use XRF for, and mining, prospecting, and geochemical exploration is a pretty common application that XRF is used for. Any element that say any mining of any particular element, there are plenty of them that come up. One question came up on halogen-free applications. Can XRF be used for halogen-free applications? I didn't talk about that too much today. That's another halogen-free, if you're not familiar, is a voluntary standard that some manufacturers have signed on to limit the amount of chlorine and bromine that are going into plastics. XRF can be used to detect those two elements, and so the short answer is yes, you can use XRF for halogen-free applications. Chlorine's a lot more difficult to test for than bromine, though. Bromine, you can get a detection limit of a few ppm within a few seconds. For chlorine, you tend to need to run a bit longer tests. Someone's asking about specific X-ray tube type in an analyzer. I only talked about tube voltage, but also the X-ray tube that's in the analyzer has what's called an anode material that'll be some element. Common ones are gold anode, rhodium anode, or silver anode. And someone's asking which anode is best for consumer products testing. In our experience, of the ones that are out there, generally gold anode or tantalum anode work very well because you have there's very little interference from those elements on any of the elements that you're testing as part of consumer products regulation. Silver anode, you do have a little bit of overlap with some cadmium lines, and if you do a direct comparison, you may find that the gold anode would do a little better than silver anode. You may find the same for rhodium anode, that a gold anode would do a little bit better, but it depends on a lot of features, not just the anode type. So see one question about XRF testing in the automotive industry. Any regulations for covering restricted elements in automotive applications, in cars basically, XRF can be used for. There is the set of ELV, end-of-life vehicle regulations in the EU that are very similar to RoHS, and yes, XRF can be used to for those applications.
Hi, Brandon. This is Joe. I see there was an earlier question regarding looking for training and inspections in China. Intertek does that. So I recorded the gentleman who asked that question. I will contact you with some information regarding what we can do is for help you with factory inspections and RTPs as far as Asia or anywhere within the world. So that's something Intertek can help you with.
And someone else is asking about surface effects. If you're testing an aluminum alloy and have an anodized layer, do you need to remove that? Do you need to remove an anodized layer, or if you have a paint layer on top? It really depends on what you're testing for. If it's a very thin layer, then you'll be able, most likely the X-rays will penetrate through it, because an anodized layer is usually very thin, only a few microns or less, usually less. And so X-rays can penetrate through that, but at that point you're testing an inhomogeneous sample, so there is going to be some shielding of the substrate, and so it may cause some deviation of your results. It's always better to remove a surface coating, but you may find that in some cases you're able to do your analysis without removing the surface coating. So the general answer is yes, you should remove surface coatings, but in some cases you don't have to.
Okay, just Joe again. There's also a question I saw that came through on the chat. Can XRF be used for SVHC testing? Substance is a very high concern for REACH. Typically, no. We depend on lab testing for SVHCs, typically because they're not the elements or compounds that are strictly that are in SVHC. So it's very difficult to check for most of the SVHCs using XRF. There's also a question regarding correlation between XRF results and wet chemistry. Typically, depending on the element and the actual product and material, we can see some correlation. But again, we want to reiterate that it's a screening technique. It's not for quantitative lab results. So if you need quantitative lab results, we recommend always going for the wet chemistry testing.
And one question about testing for aluminum and silicon in metals. You can use XRF to test for aluminum and silicon. The lightest element that you generally will see able to test for by handheld XRF is magnesium. But magnesium, aluminum, silicon, and anything heavier than that in metals or other sample types, you can use XRF to measure.
Okay, another question that came in late here is consumer products were addressed in this presentation, but you can use XRF for industrial applications such as bearings, if you're looking for certain heavy metals. And on the same line, the question regarding electronic equipment, does it need to be homogeneous? Which is yes. The answer is yes. We can screen electronics for the substances, but then we really would much rather see the substance or the element in its homogeneous state to get a true reading. Reason being, there are a lot of exemptions under electronics, such as lead and ceramics still, that we do get. We can pick up lead if it's not in a homogeneous state. So the best way for screening, again, is homogeneous. That's not to say you can't screen a printed circuit board for lead. We do that, but we'll make sure we understand what we're actually looking at as far as what the materials are made of and each component on the board.
We've got about 5 minutes left, so guys, if you want to just look over anything else additional that you might want to discuss.
Okay.
We have one question on the safety of handheld analyzers if they've been tested by a third party. I know at Innovex we test all of our handheld, or we have our handheld models tested by an independent agency for radiation profile to see what sort of radiation is coming out in which locations. Safety depends on what the regulations are for the particular for the place that you're in. So the independent third party can only tell you what your radiation levels are at different locations, and you have to apply those to the local regulations on radiation safety. But generally, you'll see that as long as the instrument's being used properly, that you're not for example, putting your hands too close to the sample analysis area, that the level of X-rays you're exposed to is no higher than background levels.
Okay, there's also a question regarding can the unit be used through a computer program, or we actually can use it hooked up to a laptop. The units are actually portable, but they can also be used within a test stand in a lab environment. And you can see the results printed on the software that's provided on the computer screen and print the report out directly from the computer. It's a very nice feature that Innovex has built into their, Olympus Innovex has built into their system. There's a question regarding some library materials based on European standards. I'm not familiar with that standard. If, Brendan, if you can take a look at that one. If not, we can get back to you on that standard.
I apologize. Which standard were they asking about specifically?
Werkstoffnummers, European.
I'm not familiar with that one. All RoHS enforcement is done by the individual member states. So the EU the EU government produces the directives, but it's up to the member states to put them into law and then enforce them. So I'm not sure if that's from a particular country or if it's a general EU document.
Yeah, I think it's a question on a library, but I think we can research that as well and get back. I'll leave it up to Brendan to talk about if he wants to talk about pricing. That's a question that came in a couple of times, I believe. So.
Yeah, that's a popular one. I'm only the technical guy. I'm the applications guy. I'd really rather not to talk about pricing. I don't want to get in trouble.
Yeah, if you have, we recommend if you have a local distributor or local dealer, they can give you all the pricing information they have for your area.
A good question on surface area that you're testing with an XRF analyzer. I can tell you for Innovex handheld instruments, the standard beam spot is a circle about 10 millimeters diameter, but we have small spot collimation available, so you can confine the beam to a smaller beam spot of 3 millimeters diameter. You do have to be careful when you're doing that, like if you're testing a circuit board, for example, because it could be that you use your analyzer to focus down to, or to collimate, I should say, down to a smaller spot size so you can just test one component and maybe not the solder joint that's next to it. But the component that you're focusing on is still not a homogeneous material. It may be a resistor or an IC chip that has a couple of layers inside. So you want to be aware that you don't want to be lulled into some false sense of security that now I'm testing a homogeneous material when in fact you're not.
Okay, also there was a question regarding can XRF easily determine if improper solder, leaded solder was used in a potable water copying piping system. Yes, it can be used in that application. Just realize that if you're using any type of brass fittings, that the gun may not be able to detect the lead in the brass and the lead in the solder. So that's one of the limitations there when you're using this for plumbing applications. I think, Brendan, there was an earlier one that I saw, the spot size, the minimum spot size of the detector, I believe 3 millimeters. Correct me if I'm wrong on that.
Yeah, the smallest that Innovex offers is 3 millimeters. Our standard spot size is 10 millimeters. And be aware that your detection limits are going to vary based on your spot size. So if you go down to a smaller spot size, your detection limits get higher because you're getting less information about your sample.
Well, we are just about out of time. On behalf of Olympus, I'd like to thank Brendan and Jishan from Olympus Innovex and Joe from Intertech for their participation in today's webinar. And thanks very much to all the event attendees. We hope this material was informative and useful. This webinar will be archived on the Olympus website at www.olympus-ims.com. Again, I want to thank everyone for participating, and we will see you again next time.